So this topic is Eisenstein criteria of irreducibility. ঠিক আছে? দেখতে পাচ্ছ তো সবাই?
হ্যাঁ স্যার, দেখা যাচ্ছে।
ঠিক আছে। বেশ। আচ্ছা, আগের দিনের so start with that problem, that is show that the polynomial fx equals to x to the power 4 minus 2x square plus 8x plus 1 belongs to qx is irreducible over q. So how could we do this? Hello? Hello? শুনতে পাচ্ছ? Hello? So the solution can be done by using the previous theorem of irreducibility in Z. That is, so if fx has a 0, if fx has a 0 in Q, then by the previous theorem, it must have a 0, in the domain of integers in Z, such that it will divide the constant term of the polynomial. It will divide the constant coefficient of fx, which is 1. And therefore, the possible zeros will be one of the divisors, plus minus 1. But if we check, we see that f of 1 is 1 to the power 4 minus 2, 1 square plus 8, 1 plus 1. So that means it is 1 minus 2 plus 8 plus 1. So therefore it is 8, which is not equal to 0. And f of minus 1 equals to minus 1 to the power 4 minus 2 minus 1 square plus 8 minus 1 plus 1. So that means 1 minus 2 minus 8 plus 1. So that is minus 8, which is again not equal to 0. And this leads to a contradiction. That is, the polynomial given above, this will not have any 0 in the field of rationals, or otherwise it must have a 0 in Z, which gives us a contradiction. Okay, so in this way we can check the irreducibility of polynomials over Qx. Now we shall move on to another famous theorem which was due to Eisenstein, and it has been named Eisenstein criteria for irreducibility over the field of rationals. Although this theorem can be extended to any quotient field of an integral domain. So the next we shall encounter with the famous Eisenstein criteria. Or the Eisenstein test. To check irreducibility. To check irreducibility over the field of rationals. Q. Although one can extend this result to any quotient field of an integral domain. But we are looking for the result here only on the field of rationals. So what is this? So what is a statement? So this is called Eisenstein's test for irreducibility. So the statement is as follows. So let us consider first a prime number. So you need to choose a prime first, a prime number p. And this is fixed. So firstly we need to choose a prime number p. Okay. And suppose that fx equals to n x to the power n plus n minus 1 x to the power n minus 1 blah 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 plus a1x plus a0 belongs to zx. That is, it is a polynomial over the domain of integers such that the coefficients will satisfy these conditions. That is, the first of all is n is not congruent to 0 modulo p. n is not congruent to 0 modulo p, that is p does not divide an, the leading coefficient of fx. This is the first condition. But p will divide all other coefficients. That is, p will divide n minus 1, n minus 2, a1, a0, all of this. For 0 less or equal to k less than n minus 1 equal to n minus 1. And the last condition is the constant term a0 is not congruent to 0 modulo p square, that is p square will not divide a naught. So we are considering a polynomial a n x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 plus a1 x plus a0 over the domain of integers, which satisfies the property that the conditions, that is an is not congruent to 0 mod p, that is p will not divide an, but p will divide all other coefficients, that is p will divide an minus 1, p will divide an minus 2, p will divide an minus 3, and so on. P will divide a1, p will divide a naught. But again, the last coefficient, the constant coefficient a naught, is not congruent to 0 mod p square, that is p square will not divide the constant coefficient. So if this polynomial will satisfy these conditions, then one can conclude that then fx is irreducible over q. So one can conclude that fx is irreducible over q. So this is a test for irreducibility over q. So how the proof goes, let us see. To show that, so we need to show that fx is irreducible over q. That is to show that fx is irreducible over q. It is enough it is enough to show that fx cannot be factored into lower degree polynomials. Lower degree polynomials in the ring of polynomials over Z. That is, it is enough to show that fx cannot be factored into lower degree polynomials in Zx due to a previous theorem which we have already discussed in our previous lecture. The theorem was this one. Let us recall that theorem. Yes, this one. That is, if fx belongs to zx, then fx factors into a product of two polynomials of lower degrees in qx if and only it has such a factorization with polynomials of the same degrees Rn as in zx. And also this one, yes, this theorem. So let us check whether this can be factored or not into lower degree polynomials in zx. If possible, let us suppose that yes, fx can be factored into two lower degree polynomials. That is br x to the power r, br minus 1 x to the power r minus 1 dot b0, and another polynomial cs x to the power s, cs minus 1 x to the power s minus 1 plus dot c naught, where this is a factorization. This is a factorization in ZX with BR not equal to 0, CS not equal to 0, and the degrees, that is R and S, must be strictly less than the degree of the polynomial fx. Okay, n. Now from the assumptions, the conditions what we have assumed in the statement, that is n is not congruent to 0 mod p and a naught is not congruent to 0 mod p square. So from that condition we have, that is, since a naught is not congruent to 0 mod p square. So what does it imply? Since this, so we must have that b naught c naught, that is product of, if we execute the product of these two polynomials, then we find that b naught c naught is the constant terms, is the constant term, b naught c naught, so which must be not equal to 0 mod p square. That is, a naught is b naught c naught, and this implies b naught is not congruent to 0 mod p, or c naught is not congruent to 0 mod p, or both, right? That either p does not divide b naught, or p does not divide c naught, or both. Now let us suppose that b naught is not congruent to 0 mod p, that is, p does not divide b naught. Then again note that the other coefficient, the leading coefficient an is not congruent to 0 mod p. So these holds. So what would be the leading coefficient if we execute the product? BR CS. So this will be the leading coefficient, and this implies, so BR is not congruent to 0 mod P, or mod P, and CS is not congruent to 0 mod P, as P being a prime. And An is the product of BR and CS. Yes. Okay. So you see that CS is not congruent to 0 mod P, this one. Now let small m be the smallest integer, the smallest positive integer for which, smallest positive integer k, for which smallest positive integer of all k's for which ck is not congruent to 0 mod p. Already we have found a coefficient cs, that is the leading coefficient of the polynomial. This is not congruent to 0 mod p. But we need to find out the smallest integer m of all those k's for which ck is not congruent to 0 mod p. And for that reason, then what we shall get, that is am, if we execute the product of these polynomials, then we find that am, that is for this am must be of the form b0cm b1cm minus 1 plus b m minus I ci or some I such that 0 less or equal to I less than m. দেখো এটা ভালো করে, এখানটা ঠিক আছে নাকি? Now b0 and cm both are not congruent to 0. Modulo p. b0 and cm are not congruent to 0 modulo p, and all other coefficients cm minus 1, cm minus 2, ci are all congruent to 0 modulo p. The reason is that since we have chosen this m as the smallest positive integer of all those k's for which ck is not congruent to 0. So all other coefficients with index less than m must be congruent to 0 modulo. So this is the reason. And this implies that, so that am is not congruent to 0 modulo p. That am is not congruent to 0 modulo p, since am will be b0cm congruent to b0cm modulo p. This. So am is not congruent to 0 modulo p. But if we see our assumptions, then we find that the only coefficient of fx which is not congruent to 0 mod p is an, because all other coefficients are all congruent to 0 mod p. So this m, so this implies this m must be n. There are no other options. So that m must be equals to n. And consequently, if it is n, so consequently what we can conclude? So we can conclude that the s, that is the index of the leading coefficient of the polynomial this. So this one equals to n, because n is the degree of the polynomial fx. So the only possibility fx এর degree হচ্ছে n. So the only possibility of CS, that is S, must be n. That is, the degree of the polynomial CS x to the power s plus dot C0 must be n. And if it is n, then this will contradict the assumption that the degree of the polynomial this is strictly less than n. So this contradicts our assumption. This contradicts our assumption that the degree of the polynomial CS x to the power s plus dot dot C0 is strictly less than n. And hence, this contradiction will conclude that hence fx, our assumption was wrong. That is, fx cannot be factored into polynomials of lower degree in the ring ZX. So this is the way of proof. So if you have any questions, please let me ask. বোঝা গেছে এটা? Hello. Hello.
হ্যাঁ স্যার, এটা বোঝা গেছে।
বোঝা গেছে, okay.
হ্যাঁ।
So let us check an example that again we consider the same polynomial x square minus 2 over qx. Then we can show that this polynomial x square minus 2 is irreducible over q, but using Eisenstein criteria. So this is another kind of proof one can impose over this polynomial using Eisenstein criteria. But how? If we consider the prime, that is, so we need to choose the prime first. So what I have already told that we need to choose a prime in such a way that it will satisfy these conditions for the given polynomial. So this is your part. That is, you need to choose a prime p which will satisfy these three conditions for that given polynomial. So this is crucial, that you need to choose a particular kind of prime which will satisfy the conditions of the
স্যার
given
প্রাইমটা
polynomial.
মানে যে প্রাইম নাম্বার যেটা চুজ করব সেইটার উপর পুরো ব্যাপারটা ডিপেন্ড করছে, তাই তো?
একদম মানে এইটাই আর কি, মানে অন্য একটা প্রাইম দিলে হয়তো সেটা মানে আমার মানে কাজটা হচ্ছে that we need to choose a particular kind of prime but it will satisfy the conditions.
মানে কন্ডিশন গুলো যে স্যাটিসফাই করবে সেটা
স্যাটিসফাই করতে হবে। হ্যাঁ, যেমন হচ্ছে ধরো এই যে এক্সাম্পলটা আমরা করছি, এখানে আমরা প্রাইমটা কি নিতে পারি, তুমি এই যে তার মানে ইট ডিপেন্ডস অন দা কোএফিসিয়েন্টস অফ দা পলিনোমিয়াল। It will give some indications that yes, you need to choose this prime. So here we can choose the prime is 2. Prime is 2. And if we rewrite the polynomial as 1 dot x square minus plus 0 dot x minus 2, then this 2, this prime will not divide 1, the leading coefficient, but it will divide 0, it will divide minus 2, and the last one is 2 square, that is prime square, the square of the prime, p square. P square is 4, and it will not divide the constant coefficient of the polynomial, that is minus 2. So we have chosen a prime which satisfies all the conditions stated in the theorem for this given polynomial. So therefore, by Eisenstein criteria, x square minus 2 is irreducible over q. This one. Let us check another example. That is, if we consider that, let us consider the polynomial fx is 25x to the power 5 minus 9x to the power 4 plus 3x square minus 12 over q. Then show that this polynomial is irreducible. Over q by using Eisenstein criteria. So what would be the prime for this case?
3 হবে,
বলো।
3 হবে, মানে p equal to 3.
3. This is 3. So let p equals to 3. So then 3 will not divide 25, but 3 will divide minus 9, 3 will divide 3, 3 will divide minus 12, but again 3 square is 9, which doesn't divide minus 12. So this satisfies the conditions of the Eisenstein criteria, and hence it is irreducible over q. Now another example is, let us consider a polynomial. which is of the form phi px is x to the power p minus 1 by x minus 1. That is, it will take the form x to the power p minus 1 plus x to the power p minus 2 x plus 1, where p is a prime over the field of rationals Q. So you need to check that this is irreducible over Q. Show that this is irreducible over Q. But how it can be shown? Because here only coefficients are 1. This is 1, this is 1, this is 1. So each coefficient is 1. So what is your prime? Yes. So we shall consider the polynomial phi p x plus 1. So this is a trick to show that this polynomial is irreducible, this one, phi p x. So this is a crucial trick. That is phi p, we need to consider this polynomial phi p x plus 1. And then if we consider this polynomial, then it will give, that is phi p x plus 1 will be x plus 1 to the power p minus 1 by x plus 1 minus 1. And if we calculate, then what will happen? That is, it will be, the numerator is x to the power p plus 1 plus pc1 x to the power p minus 1 and dot 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 px by x. That means it is x to the power p minus 1 plus p1 x to the power p minus 2 dot plus p. So this, so considering this polynomial, we are getting some indications that yes, what will be the prime we need to choose. So if we consider, if we choose the prime p for our Eisenstein test, then we see that this p will not divide the leading coefficient of phi px plus 1, that is, this is 1, but it will divide e1, it will divide the next, what will be the next coefficient? PC2 and so on. It will divide P. And again, but P square will not divide the constant coefficient P. And so hence why the Eisenstein test, we conclude that the polynomial phi p x plus 1 is irreducible. over Q. So we have shown that this polynomial, what we have considered, is irreducible over Q. This one is irreducible. Now we shall show that the given polynomial phi px must be irreducible by using the irreducibility of this polynomial. But what is the logic? That is, if phi px can be factored hx gx, that if phi px equals to the product of two polynomials hx gx, that is phi px equal to this, a non-trivial factorization. Non-trivial factorization of phi px in zx, in the ring zx over z. Then the polynomial what we have considered phi px plus 1, then it will give that phi px plus 1 must be hx plus 1 or x plus 1. And this will give a non-trivial factorization of phi px plus 1 in the same ring zx over the domain of integers. But what we have shown earlier, that this polynomial phi px plus 1 is irreducible over Q. That is, it is also irreducible over zx. Right? So this a contradiction. And hence our assumption about this polynomial was wrong. Phi px. That is, phi px must be irreducible over Q. So for that example, you must observe that for this polynomial phi px, you can't choose any prime, although it is irreducible. We have shown this irreducibility of this polynomial via the irreducibility of phi px plus 1. Right? Now, the following example, let x is 8x cube plus 6x square minus 9x plus 24 belongs to zx. Then what will be the prime for this polynomial? What is the prime? We need to choose.
প্রাইম 3 হবে।
Yes.
আচ্ছা 3 নিলে তো হবে।
3. So if we consider p equal to 3, then 3 does not divide 8, but this one, but 3 will divide 6, 3 will divide minus 9, and 3 will divide 20. But 3 square equals to 9, which will not divide this constant coefficient. So in this case also, we have shown that fx is irreducible over Q by the Eisenstein test. Okay, so I'm giving some problems for further discussions. That is, let number one is let fx is x to the power 6 plus 3x to the power 5 plus 4x square minus 3x plus 2, and gx will be x square plus 2x minus 3. Okay, these are okay. Acha. The two polynomials over Z7. Now find their quotients Qx and Rx in Z7. Z7x. Sorry. Another problem is show that the polynomial x to the power 4 plus 4 can be factored into linear factors in the ring Z5x. Now observe that this polynomial cannot be factored in Q. This cannot be factored in Q. So what is your conclusion in Q? Number 3 is so that fx equal to x square plus 8x minus 2 is irreducible over Q. Now another question is fx irreducible over R? Support your answer. Support your answer. The next problem is check irreducibility. Number 1 is irreducibility over Q. X square minus 12, 2x to the power 10 minus 25x cube plus 10x square minus 30. Number 3, 4x to the power 10 minus 9x cube plus 24x minus 18. Number 5, show that the polynomial x to the power p plus a constant a in the ring ZPX is not irreducible or any member A belongs to ZP. this. There are many problems, but ওগুলো পরে পাঠিয়ে দেবো, ঠিক আছে? মাস্টার করো। Now we move forward to the discussion on the ideals in fx. Ideals in fx. Because these ideals, a particular kind of important ideals, will give you the quotient rings which are going to be a field. So one may observe that the ring fx over a field f, so it has a rich algebraic structure as in particular fx satisfies most of the ring theoretic features that are enjoyed by the ring of integers. One important property that both the rings have is the division algorithm. That we can have division algorithm in Z, and we have also proved it in fx2. And using this division algorithm, one can have many properties that are common to both Z and fx. And our next discussion, so another important property which Z enjoys is now recall that in the ring of integers Z, the ideals are of the form nz, right? That is the multiples of n r belongs to Z. So the ideals are of the form nz in the ring of integers Z. So the ideals are of the form nz. So this is a special kind of ideals that this ring has. Now in the case of fx, we will see the same kind of feature fx enjoys. That is, every ideal of fx will be generated by a single non-zero polynomial. Okay. So every non-zero ideal of fx or any ideal of fx can be generated by a single polynomial. So our next discussion will show that will show that any ideal in fx will be generated by a single polynomial. Which was the case we have proved for the ring of integers z. That is, every ideal in z can be generated by a single integer. That is of the form nz. That is, this ideal is generated by this n. And also, it is to be noted that we will have another important feature. We will have unique factorizations. In fx, we will have unique factorizations in fx as in the case of the ring of integers, as in the ring of integers z. That is, in z every integer can be expressed, what was the theorem? Every integer can be expressed as a product of powers of primes. Right? Okay. So now we need to recall the following definitions in a commutative ring R with unity. So the definition is, so let R be a commutative ring with unity 1 and consider an element of the ring A. So one can recall that the non-empty set R belongs to the ring R, capital R. So this set forms an ideal in R containing A. This ideal is defined to be the principal ideal generated by small a. And we shall denote it and denoted by L angle A R angle. This. Now an ideal I of R is said to be a principal ideal, an ideal I of R. An ideal I of R is said to be a principal ideal in R if you can find an element A in the ring R satisfies that ideal I will be generated by A. That is, an ideal I is said to be a principal ideal in R if we can find an element A in the ring such that ideal I will be generated by a single element A. So then you can say that I is a principal ideal. Now, a commutative ring R with unity 1 is said to be a principal ideal ring, or simply in the abbreviated form said to be PIR, that is principal ideal ring, principal ideal ring. If every ideal of R is a principal ideal. Okay. In addition, if it is an integral domain, if it is an integral domain, then we shall call this a principal ideal domain. Or simply in abbreviated form PID. PID. For example, the ring of integers. The ring of integers, it is an integral domain in which every ideal can be generated by a single element. That is, every ideal is a principal ideal. So the ring of integers is an example of a PID. Okay. Also, you can have in effects that if we consider a polynomial, a non-zero polynomial, non-constant polynomial, that is the ideal generated by x, it is a principal ideal. Principal ideal in fx. So consider any polynomial, then the ideal generated by that polynomial will be a principal ideal. So there are many examples. But what is important is the following. That is, we have to show that every ideal in fx is principal. Every ideal in fx is a principal ideal. Is a principal ideal. That is the integral domain fx is a PID. So we have another PID which is fx. So you need to show that every ideal in fx is principal ideal. So how the proof looks like? So let us consider an ideal. Hello. So let I be an ideal in fx. So two cases may arise. The first one is if this ideal is a zero ideal, that is, it is generated by only the zero polynomial. So if this ideal is a zero ideal, then I is generated by the polynomial 0. So therefore it is a principal ideal. So every 0 ideal is principal. So there is nothing to prove. So let us suppose that I is not a 0 ideal. And so we can consider a non-zero polynomial. Gx belongs to I. So we can consider a non-zero polynomial Gx belongs to I. And then one may choose a non-zero polynomial. One may choose a non-zero polynomial Hx belongs to I, but having an extra condition, which is having least degree. That is, we can choose a polynomial in I having least degree. But how can I choose this polynomial? Due to Weyl ordering principle. Often. Due to Weyl ordering principle of n, which can be applied to the degrees, of those non-zero polynomials staying at I, staying at the ideal I. So we are considering the degrees of all those non-zero polynomials staying at I, and then we have the non-zero polynomial in I having the least degree by the Weyl ordering principle. Okay. Now, two cases may arise for this Hx. Now it may happen that the degree of that polynomial hx may be 0. And so the the 0 degree polynomial must be a non-constant, a non-zero constant. So this 0 degree polynomial must be a non-zero constant, belongs to the field. The constant belongs to the field F. And being a field and being non-zero, this hx, sorry, this is hx. This hx must be a unit. That is, it has a multiplicative inverse in fx. And if an ideal contains a unit, then that ideal must be equal to the whole ring. That is, this I must be coincide with that fx. Okay. And this is generated by the constant polynomial 1, which says that I is principal. Okay. And if we consider the another case, that is whenever the degree of hx is not 0, that is if degree of hx is greater than equal to 1, and let us consider any polynomial fx lying at I. So be any polynomial. Be any polynomial in I. Then by applying division algorithm, there exist two unique polynomials. Two unique polynomials qx, rx, such that fx is equal to hx, qx plus rx, where 0 less or equal to degree of rx is strictly less than degree of hx. Now note that fx belongs to I, hx belongs to I, and this will imply that fx minus hx qx must be in I, as I being an ideal in fx. And this implies this fx minus hx qx will be rx. That is, rx belongs to I. Rx belongs to I, with the property that degree of rx 0 less or equal to degree of rx strictly less than degree of hx. So if degree of rx is